All right. So I will, as Paula said, present my my work during Brno, my stay in Brno, or part of it, that it was the text-dependent speaker verification system that we submitted for the SdSV challenge. I'm not sure whether the audience will be familiar with all the terms because it's quite technical and specific of speaker recognition. So if you have any questions, I will try to at least introduce in one sentence some of the concepts, but if you have any questions, you can tell me if I need to go a bit further into details. So the outline of the presentation is that I will make a small introduction about the topic of myself. Then I will present each of the components that we submitted for the SdSV challenge at BUT. And show the evaluation results. And then I will continue with some post-analysis on different systems and the conclusions. So, well, about myself, Paola already introduced me, but basically I did my studies until the PhD in Universidad Autónoma de Madrid in Spain. And during my PhD,
Excuse me, Alicia, are you showing different slides, or are you still in the first slide?
I'm showing different slides.
I mean, I can only see the first one. Is everybody seeing the first one, or?
Yes, I think you might try to minimize, like stop the sharing.
Stop I think I need
presentation mode and start again. Sometimes it happens. I don't know why. Good catch, Loriana.
Yeah, it was good that you tell me now that. Okay, maybe I can actually share the desktop and then.
Okay, can you try to switch page?
Now yeah.
Yeah, I see. Yes, now it's moving. Hopefully.
Yeah.
Okay.
Now it's good.
Okay.
Yeah.
So this is I don't know if you see this, but okay. So this was the outline. Then my background is here. So basically, I studied at the University Autónoma de Madrid. And during my PhD, I was visiting Brno and SRI, and then I went back to Brno for a postdoc under the project with a Marie Curie fellowship. And I was there for 2 years, almost 2 years, and I came back to Spain actually like a month ago. And I am now currently assistant professor at the Universidad Autónoma de Madrid, again, at the Audias Research Group. So about the challenge, I will be briefly describing the challenge. So the challenge is based on short duration speaker verification. It was organized in such a way that it had 2 tasks. One of them was text dependent, in which for those who are not familiar with speaker verification that much, here we try to verify not just the speaker, but also that the phrase content in the utterance is correct. Then so in this case, we have different non-target trials. One of them is when we have a speaker that is an impostor and the correct phrase. Then when we have the target speaker but and wrong phrase, and then we have impostor speaker and wrong phrase. So these 3 are considered non-target trials. We have 3 enrollment utterances and 1 test. And the data set is based on 10 different phrases. So it is a limited number of phrases and is fixed. Then there was another task, which was a text independent. And here the task would be to identify the speaker and not caring about the content of the recording. But I will focus on the text dependent system, which was the best performing system for the challenge in text dependent. So we basically were allowed to use some out-of-domain data, libre speech and voxelab, and then some part of the DeepMind, which was considered the in-domain data. We just basically split it, and these are the summary of what the data set is based on. And this is the in-domain data, and we call it SdSV through the presentation. The experimental framework that we used, well, basically these are details for the evaluation, but we split it into training and development with separate sets of speakers. And we just tried to simulate basically what the prior knowledge for the tested was, which was basically not containing or containing very few of the impostor wrong phrase non-target trials, because these are supposed to be the easy identify non-target trials. So for the rest of the results, basically we focus on both impostor speaker and correct phrase, or target speaker and wrong phrase. So the system that we submitted, the overview is the following. So we have as front end basically embedding structures, either based on iVector or XVector. And then combined with the backend, depending on the system, we have phrase-dependent PLDA, heavy tail PLDA. We perform score normalization, and then we combine it with a phrase recognizer through some score level fusion based on logistic regression. I will explain each of the components in the following slides. So basically, for those that are not that familiar with the terms, XVector and iVectors are basically a representation of the audio recording in a fixed length vector, low dimensional in general, and the XVector based embeddings are extracted from a DNN, basically a neural network that is trying to classify speakers. And then we take the output of one of the layers, and that would represent our speaker in a single vector, the recording basically. While iVectors come from a generative model in which we have it's trained unsupervisedly somehow, and we have the low dimensional vector, which is basically an estimation of a latent variable in that generative model. And it tries to capture the variability in the data set. So the motivation to use these two kinds of embeddings, basically the XVectors are the best right now for text-independent speaker verification. They require a large amount of data to train. And we saw that some other previous work on text-dependent, we saw that it was better to train only on in-domain data. But let's see what for us worked. So and then on the other hand, the embeddings based on iVectors, we chose these ones as well because it was used for text-independent many years ago. I mean, not many years ago, but for many years and a few years ago. But currently they are worse than the XVectors. However, for text-dependent, when they were trained on features that involve bottleneck features, so it was a concatenation between bottleneck features and MFCCs, it actually showed better performance than for text-dependent. So we just analyzed these two embeddings. The voxel, the XVector structures, basically we train them for the challenge in two different data sets. So either out of domain voxel or in domain SdSV data. For the voxel system, we had the standard TDNN model, which was our voxel system, voxel challenge system. And it was trained to classify speakers with the architecture that I'm showing here. So basically TDNN model and 512 dimensional XVectors. On the ones that we trained for with the in-domain data, what we did was to use, instead of classification just for the speaker identities, since we have the information about the phrase contained in the recording, we trained for speaker ID and phrase information. So basically we had 10 times more classes than in the other one. This one obviously was trained on the in-domain data, and it was another TDNN based system, in this case factorized TDNN. For the iVector structure, so what we used was the concatenated features, MFCCs and bottlenecks. So basically the bottlenecks are features that we extract, is frame level features that we extract from a network which is trained to classify phoneme states, basically. So they are supposed to contain information about the message that it is in the recording. All our I-vector structures were trained on the in-domain data and using the UVM 1000 dimensional with 1000 Gaussian components. The difference between the I-vector structures that we use for the final system were basically whether in the training of the bottleneck features or the dimensionality of the I-vectors. So we had 4 of them. Basically in this, well, I don't know if you see my mouse, but basically in the X-vector structures, the data set meant in which data set we train the X-vector structure. In this case, the I-vector structure is trained on the in-domain data, but the bottleneck feature structure is trained on either library speech or the in-domain data. So we had 2 I-vector structures, which are trained on library speech, which is English audiobooks, basically, read speech, and it's in English. And we had 2-dimensionality of the X-vector, of the I-vector, sorry, and they were trained on a stack bottlenecks. So it's one architecture for the bottleneck structure. Then we have another structure which was trained only on the in-domain data. In this case, we have smaller I-vectors, and we train on the in-domain data, which has these 10 fixed phrases, 5 in Farsi and 5 in English. And finally, we have another bottleneck feature structure trained on library speech and in-domain data. So basically, we train with English and the 10 phrases that are English and Farsi. And for this I-vector structure, we have also like a different architecture of the bottleneck feature structure. But for the rest, it was also 400-dimensional I-vector. With respect to the backends, so basically the usual backend for speaker text-independent speaker verification is PLDA. So it's a model that basically gives us a way to, we train it, and it gives us a way to compare 2 utterances and do the scoring. And in our case, what we did was to train specific PLDA models for each phrase. So we call it phrase-dependent PLDA. And we have, for each of the 10 phrases, we have a different PLDA. And then what we did during testing, it was to, for each trial, we basically score that trial depending on the phrase contained in the enrollment. For some of the X-vector structures, we use heavy-tail PLDA, which worked, performed a bit better than, well, not better, but it gave us some improvement with the fusion. Which heavy-tail PLDA is basically PLDA assuming instead of Gaussian distribution for the priors, we assume student distribution. Then we also tried this phrase-dependent heavy-tail PLDA, but it didn't really outperform for us the standard single global heavy-tail PLDA for this case in these systems. Then for the backend as well, we perform score normalization on top of the scores that the PLDA or phrase PLDA model outputs. For the system submitted for the challenge, we basically use score normalization just for the phrase-dependent PLDA, and we also perform this normalization depending on the phrase. And what we saw is that we could basically remove the error for the trials in which we have the wrong phrase just using some phrase recognizer, which basically is we used a classifier and Gaussian linear classifier, in which we just score and basically classify among the 10 phrases, because it was a fixed set of 10 phrases. This classifier was used to produce soft scores, so it didn't give us hard decisions on the classification, and we combined these scores with the outputs of the speaker verification. We have more details in the paper in Interspeech, where we presented this system. And then finally, for the score fusion, we used the standard logistic regression, and we trained on the development set, but basically we saw the same improvements or the same trends in the evaluation set. So here is the table of the results that we have for the 8 individual systems, and then the fusions we perform. And I will be commenting on them in the next slides. Basically, we have the scores, the performance for the leaderboard and the performance for the development set. And we have the scores with and without and with normalization, and the combination of both. And these are mean DCF times 100. And so basically it's is error, so the lower the better. And I will go through the table in the next slides. So we have the for the individual systems. First, we saw that AS norm was helping in most of the cases, and then we got some further improvement when combining the scores from non-normalized scores and AS normalized scores. We just did some logistic regression, linear fusion, and we performed some experiments that we need to still go deeper into it, but I will not present here. But basically, our hypothesis was that it was helping with calibration for the different target phrases. And we consider this combination of unnormalized and normalized scores as a single system, since it is still using the same, basically the same front end and back end. It was just the combination of the scores. So in our case, I vectors were consistently better than X vectors for the task. And our best single system was actually based on I vectors and bottleneck trained on LibreSpeech and 800-dimensional I vectors. For us, the X vectors that were trained on in-domain data were worse than the ones trained on the out-of-domain data, voxel, as you can see in this, which was actually what was in some other works was seen. What we did for the fusion basically was, again, logistic regression fusion, and we did a greedy approach. So we were adding the best single system one at each time. And we basically submitted the fusion of these 8 systems, which gave us further improvement. But actually, when we performed the fusion of just 2 systems, the performance was already quite similar, let's say. So it was, the thing is that these 2 systems that we fused, which was these first 2, were quite diverse. So one was I vector with bottlenecks that are trained on LibreSpeech, and the other was X vector trained on voxel. So we think that, fusing those 2 that are quite complementary gave us quite some improvement. During the eval time, we basically submitted this other system. So if you see the leaderboard from the website, this would be the result. The thing is that this one included some 3 systems, and we didn't see that much improvement. So basically in this presentation and in the Interspeech paper, we just describe the 8 systems, because this was just 3 more systems that have different configuration parameters, but basically different dimensions of I-vectors, GMM, or whatever. So these were the results for the final system submitted to the challenge. We are this team 56. So basically the second and third team are quite close to us. And if we see, actually, this was the analysis that they provided us from the challenge. And if we see that the death curves, or we see that it depends on where operative point we check, the curves were pretty close, or even our team, which was the blue one, was outperforming in some other points of the curve. And they asked us also to provide a best single system, which for us was I-vectors. And in this case, actually, another team outperformed our best single system, and this was based on X vectors. So we are trying to further analyze that. And this is the same analysis, but for the single system instead of the fusions. So I will start now with the analysis. First of all, I will present the analysis on the backend. So basically the comparison between this global PLDA and phrase-dependent PLDA. I will use for this case the I-vector system, our best single system. So if we compare, for example, the first and second row, we have global PLDA and phrase-dependent PLDA. And we have here, this is for the development, and we have here all the non-target trials, so this would be the whole development set. Then when we consider only impostor correct, so we have the correct phrase, but impostor speaker, and only considering the non-targets as the target speaker and wrong phrase. So what we see is that standard PLDA, which is trying to discriminate between both speakers and phrases, is this first row, and it was outperformed by the phrase-dependent PLDA in impostor correct. So basically, the phrase-dependent PLDA is trained to discriminate between speakers, but assuming that the correct phrase is there. So that's why, because we test only with the PLDA that the enrollment phrase had. So this is why we see that we got improvements in impostor correct, but actually it degrades the performance on the target wrong, because it is assuming that the phrase is correct, and in this case, it's actually the opposite case. So what we did for this is to add the phrase recognizer that I mentioned before, which basically we combined scores with this phrase recognizer that what we got is to basically zero almost the error. It was, as I said, a fixed set of 10 phrases, and we managed to almost zero the error on target wrong trials, and the performance on impostor correct basically were pretty much the same as not applying this phrase recognizer. So basically we consider that the target wrong trials can be basically discarded with this phrase recognizer. So now the analysis, I will mostly show the results when considering only the impostor correct phrase non-target trials. So here what I present is the difference in the score, how we perform the scoring of the recordings of the I-vectors in this case. So basically this is the per phrase phrase-dependent PLDA with by the book scoring. Then the global PLDA, as I showed before. This was by the book scoring, is was what we were using in the previous systems. And then we have PLDA, but taking basically the 3 enrollment utterances separately and averaging the scores. And then we compare with previous backends, because basically previous works didn't have enough data to train a PLDA model basically for the backend. And that's why we compare with cosine scoring, which was used before. Either applying LDA beforehand, which actually for PLDA, we also do LDA reduction and then PLDA. But we compare whether with LDA dimensionality reduction with cosine scoring and just simple cosine scoring, just dot product of the length normalized I vectors. So what we see is that, again, what I mentioned before is that per phrase dependent PLDA is still the best one for impostor correct non-target trials. But if we compare the normal global PLDA with by the book scoring, is actually outperformed by the cosine scoring. So it's still better than global PLDA, this cosine scoring, which was what it was being used before the PLDA, before in some other previous works. So it's still better than global PLDA, but it doesn't manage to outperform the phrase-dependent PLDA. And here what I added was, instead of this I vector system that it was with the bottlenecks trained on English, on Libre speech, I added here the same results, but for the system in which we train with Libre speech in English and SdSV data, which has English and Farsi. So in this case, when we basically include the information of the in-domain data in the bottleneck, in this case, PLDA actually outperforms the cosine scoring. So we didn't see the same trend when we have or not encoded the information of the sentence somehow in the system. Then what we did, for us, I vectors were working the best. So we are trying to explore a bit more the X vectors. The X vectors that we were using for the evaluation were based on basically TDNN variations of networks. And then here I tried ResNet architecture to train the X vector structure. I compared different architectures. So this ResNet 152, ResNet 34, so bigger and smaller model. Then training again with voxeleb or in-domain data, and to classify whether to classify just the speakers or a speaker plus utterance IDs, which we can do for the in-domain data. And also I will show just one experiment with either training with this additive margin loss or the normal softmax, linear softmax. So again, I'm not considering the target run trials due to this combination with the phrase recognizer that we can perform and forget about them basically for the performance. So here I have the 3 systems that we have for the evaluation, our best single system and the 2 X vectors based on TDNN. And here are the new experiments with ResNet. So this is trained on voxeleb. The second one is trained on the in-domain data, but just to classify speakers. Then train on the in-domain data, but to classify speaker plus utterance. And then in-domain data train with, instead of angular margin, we have the softmax. And then the smaller model. These were 152 ResNet, and this is the ResNet 34. And this would be equivalent to this one, but just a smaller model. So I will go through them in the next slides. what we see is that we still have better result with the I vectors. So we are trying to still improve our X vectors. But so far, what we see is that our I vector system is still better. And even if we, if we compare, I mean, these two perform pretty much the same. AS norm behaves a bit differently. So in this case, it doesn't help. In this case, it does. So these two could be considered basically equivalent in terms of performance, and still don't outperform the I vectors. When we compare the TDNN-based X vectors and the ResNet for equivalent experiments, or for example, when training in out of domain data, we see that the ResNet X vectors seem to outperform this TDNN base. So this would be the comparison. And still the ResNet X vectors are half of the size. So they are 256 dimensional, while the previous ones were 512. And we see the same when training in domain data. And in this case, it was also trained for speaker and utterance ID. So these two lines could be comparable in the sense that we change the architecture of the X vector structures. And still we see that they outperform, in this case, a bit more, even further, the previous X vectors that we had for the challenge. Then what we wanted to analyze a bit further is also how important the content that the bottleneck features carry are in the results. So basically, when we compare the I vector structure trained on library speech and both and in domain, and what we see is that with global PLDA in this case, in the impostor correct target non-target trials, or the data set that considers just these ones, basically we see a slight degradation on the results when using just in-domain data with respect to the other two. But training actually with both library speech and in-domain data provides quite similar performance. But the thing is that these two are not directly comparable, I would say, because this was a bigger total variability space, so basically bigger I vectors, while here we have 400 dimensional I vectors, but basically we got pretty much the same performance. And overall, for example, when using, this was using global PLDA, so here we are not separating in the backend depending on the enrollment phrase. But when we use basically phrase-dependent PLDA as backend, we see here with without the phrase recognizer and with the phrase recognizer. But we basically, what we see is that the phrase-dependent PLDA with phrase recognizer, in this case, the ones with library speech and in-domain data, the bottlenecks that contain both, or that are trained in both data sets, perform a bit better. But again, a bit better just when we don't normalize the scores. But since for the last system, we basically combined these two, the performance was pretty much the same, or even a bit better in this one. So that's why we chose this one as best single system. But basically, the three of them perform quite similar when we combine normalized and unnormalized scores. So then we wanted to see also this, when we include this information somehow, the in-domain data for the X vector structures. In this case, I'm showing again the target wrong non-target trials, just to see the influence of this, whether including in-domain data actually change something for this type of trials. But let's say that in the previous experiments, and in the rest, this could be solved with a phrase recognizer. But let's say that we don't have the phrase recognizer because we don't have a fixed set of sentences, for example. So we can see here that comparing this would be the TDNN X vectors and these three ResNet S vectors, the last experiments I showed before. So what we see is that the ResNet, when it is trained just to classify speakers, and the other two that are in out of domain data, so basically they don't have any information about the 10 phrases, which actually are different. 5 of them are in Farsi, not in English, while Voxalep is mostly English. The TDNN is a bit more robust, I would say, but still very bad performance in the target-run trials. ASNorm also made the results worse in general for these target-run trials. So it was not it doesn't perform well for the target-run trials. And then what we saw is that for any X vector structure that is trained just to classify speakers, the results were very bad, especially for ResNets. They were very bad in target-run. But when we train on the in-domain data and to classify both the speaker and utterance, we are giving the network the information about the utterance, about the phrase, then we get a huge improvement with respect to the previous systems. Still, ASNorm make the results a bit worse, but we saw a huge improvement. So this was much better in this, but as I said before, what we are trying to improve is basically this, when we consider that the phrase recognizer would basically take care of the target-run trials. So in this case, we see different comparison. In this case, for the impostor correct, basically we see that ResNets are better than TDNNs, and the out of domain in this case, for example, outperform the others. This changed a bit with the phrase-dependent PLDA, but for global PLDA, we have this. So this would be the analysis and the system that we submitted, and then the analysis we did after the evaluation. So I will just summarize some of the conclusions. From the evaluation, we basically had the best performing system, our Fusion, and for us, the iVector was the best. But as I mentioned, the second best system had just X vectors, and they were pretty close to us. Then with the amount of data that they gave us, they provided for training, we could study some of the techniques that are effective in text independent, basically speaker verification, such as X vectors. And we found that X vectors trained on out of domain outperform the ones that are in domain data. This was in the evaluation. Then training PLDA backends, depending on the phrase that we have, gave us further improvement. And we could train these models also due to the amount of data that they gave us for training. These previous works were based basically in cosine similarity. So and we saw that phrase-dependent PLDA outperformed cosine distance. So the combination between phrase-dependent PLDA and the phrase recognizer, the score combination of those two, gave us 63% relative improvement over global standard PLDA. And the Fusion provided us with some further improvement on evaluation. And even though it was 8 systems, just with 2 that are very different, then we already got quite some improvement with the combination. Finally, from the post-eval analysis, what we can see is that the phrase-dependent PLDA keeps outperforming even for ResNets and other models that we tried. Outperforms the common cosine scoring backend that was used previously. ResNet X vectors seem to work better than the TDNN counterparts, and still with lower dimensionality. So that was a good solution, a good way to then have smaller PLDA as well. Then different bottleneck features perform similar. So even when we include in-domain data, which includes also English and Farsi, they still perform about the same. And training the X vector extractor for speaker and utterance identification performs well even for target wrong trials, which was not the case for the other X vectors, but still worse than using the phrase recognizer. And some further ideas that we are exploring. So basically, I-vector systems that use VoxLab or LibreSpeech, for example, out of domain data. First results were not better than using just the in-domain data. So it doesn't really follow so far the trend of X vectors that the more data, the better, and even if it's out of domain. Bottleneck features for X vector extractors. We want to explore this because it works for I vectors, and we want to see how to, if the network is basically able to extract information from the content of the sentence, which is important for the text-dependent case. Then analyze a bit more this combination of unnormalized and normalized scores with respect to calibration of the systems, if we can just solve it with the calibration. And then try to train the X vector extractor, not just considering a speaker utterance as one class, but having speaker ID and phrase ID in the same training of the X vectors, for example, as it was done for multi-language data sets. So this would be everything from my side. So thank you very much for inviting me and for your attention, and I'll be happy to answer any questions that you may have. Thank you.
Cool. Thank you very much for your talk. Are there any questions or comments, please?
Hey, Alicia. This is Kevin. Thanks for a nice talk. So I'm not too familiar with the adaptive normalization technique. I'm wondering if you can explain it in a little bit more technical detail for people not in this field, because it seems like it could be generally applicable.
Yeah, I think so. Basically, what we have is a cohort of, so we have some set of utterances, and you just basically normalize you score your system against those. And basically you normalize the scores in a symmetric way. So you perform Z norm and T norm. So basically considering the scores against models or tests, and then average. So it's already on the score level, and you just basically transform them, find the factors that transform those scores to get better calibration usually.
Okay. And is this commonly used in this field?
For a speaker, yeah, for speaker
Okay.
verification, it's quite common.
Okay, got it.
Any questions or comments, please? I guess someone's trying to speak.
Yes, I had a question. So you use the by the book PLDA, which usually works worse than just averaging the I vectors or doing averaging the scores. So what's your intuition of why for this task doing the by the book PLDA work better?
Yeah, I'm not really sure why. So basically, we didn't try the average in the I vectors, which we don't know exactly how it performed. That's a good point. And I don't really know why in this case it performs. I don't know if it's the case also for phrase dependent, for text dependent or text independent. I'm not so familiar with this comparison for text dependent, so that might be, but I'm not really sure. So here we do have the enrollment, which are 3 sentences that are the same. But I don't know, I didn't explore further that. If you have any intuition that as an expert in this PLDA.
No,
I don't know if Lucas has, because Lucas is around and he was also working on this challenge. I don't know if he has.
Yeah, well, perhaps the only intuition is that usually the by the book scoring doesn't. I mean, we suspect that the by the book scoring doesn't work because the trials are not statistically independent. So the by the book scoring would expect that the trials would be the enrollment utterances would be statistically independent, and maybe it is more the case in this sense, in this case, because I think always these 3 enrollment utterances were taken from 3 independent sessions. So maybe this is something that, but I mean, this is just intuition. So perhaps better matches the assumptions of by the book scoring.
Okay. Another question is about I vectors versus S vectors. So you have many results where I vectors are better than S vectors, which is quite unusual with the latest publications. So do you have also some intuition of why I vectors are still doing good in the test dependent?
Yeah, I have that question too. Yeah, I agree.
Yeah, so the thing is that it is true that these bottleneck features work quite well for language ID, even on top of I vectors, basically. So my intuition is that the I vector is able to extract more information from those than the X vector itself, even if you try to classify at the same time speakers and utterances. But it is true that our best I vectors were still worse than the best X vectors from the second best team, but I still didn't manage to replicate the results, and they were pretty similar. So still, we wouldn't see this difference that we see in text-independent speaker verification, that X vectors outperform widely the I vectors. But I guess that my intuition is that that's why I wanted to try to include somehow these bottleneck features in the X vector structures, because I don't know whether the bottleneck features are containing a lot of information about this content of the phrase. And since it is text dependent, then you have to be aware of that, or what's the reason. But yeah, it is true. But we use them because they were performing quite well in previous works. And for us, still they outperform the X vectors. So I will, let's see if the bottlenecks are the key, or is just the generative model on top of the bottlenecks, basically. That could be as well.
Maybe if I can try to add something to that. I mean, of course, I mean, this is all just guessing, but the for text independent, you need to make things robust to. I mean, I guess that the largest source of variability is the phonetic content, and here you don't have this problem. So perhaps I vectors are still fine because maybe here we don't have that much data, so it's easier to train it, and maybe they are still fine because you don't need to train things discriminatively to remove the information about the phonetic content, and they just because it's text dependent, they are still quite powerful. And still we had to use this phrase dependent PLDA, so you can see that for each phrase we actually have different distribution of speakers and within and across speaker variability we have to use different PLDA for. So and actually for X vectors we didn't need that, so you can see that X vectors take care of this variability. But if you have the comfort to for each possible phrase to train different model which discriminate between speakers, and then then I vector seems to be good enough. So you can see that the X vectors eventually remove some of the more of the unwanted variability, but here we had to build a special model for it, which at the end, so we had to build a specific model for each phrase, but then in that case, the I vector still works good enough and better than X vectors, maybe because you don't need that much data to train it.
Thank you.
So Alicia, one comment or just observation is that, when you look at text-dependent speaker ID, there is this temptation to think that just like these people in forensics and law enforcement do, you want to focus on phonetic effects and how individual speakers might pronounce certain phones and sounds and this and that. And of course, all of us seem to have given up on those methods. We just go build our I vectors or X vectors and then crank the crank. But I'm wondering whether this isn't a data set on which we should look more. And so, when Jesus was asking why I vectors work well, I was thinking more or less what Lukáš said, that they probably not just that I vectors work well, but that I vectors along with these bottleneck features work well because they were trained for doing speech recognition. So they're extracting phonetic information. So I'm wondering whether, first of all, did you guys try more? And if not, what kind of things could you try? And I'll give you an example of that. So, if I took these phrase-dependent PLDAs, clearly the mismatched PLDA doesn't do well. But if we plotted a matrix, could we see that two phrases that share more phonemes are actually also, less affected by the wrong PLDA? Is it that maybe we need to focus on certain types of phonemes? Do we need to focus on vowels or stop releases? I don't know. I'm just thinking that this is an opportunity to sort of go back and ask ourselves, it's fine for I vectors, X vectors to perform at whatever 3%, 2% error rate, but can we explain to someone what's going on?
Yeah,
yeah, go ahead.
No, I was going to say that, actually Lukáš and Hussein, which was the organizer of this. So the thing is that also for this, we were training on, for example, the bottlenecks on English, while the phrases are English and Farsi. So even though, and we saw that it didn't outperform that much just training on the Farsi, also because it's a very reduced. So basically for Farsi, we have just 10 sentences, 10 phrases. So then we don't have that much variability in terms of phoneme. But I know that Lukáš with Hussein and so on, they had some more systems, and one of the baselines for the challenge was this based on HMM instead of GMM, UVM, I vectors. Basically, they were using HMM in order to take into account this sentence, basically, so more closer to ASR and so on. But probably Lukáš has even more insights on that.
Well, I didn't really get what Sanjeev, what were you suggesting that?
So what I'm suggesting, for example, is can we say that the system is paying attention to certain segments of the evidence? It's paying attention to some phonemes or some diphones or some set of cues, which perhaps are consistent with how human analysts would do speaker recognition or speaker verification and say, hey, so there are these people who are trained to do voice recognition, and they do this analysis where they align the data and look at various regions of interest.
Well,
so
that I don't know what exactly that is paying attention to. So the fact that we combination with the bottleneck features works well means that they eventually the system eventually likes to condition somehow also on phonemes. So you need to cluster things by phonemes, and basically you have to split the acoustic space somehow also by phonemes, and the phonetic information there seems to be important. So here one could say that the bottleneck features, which really contains information about phonetic information, then they are important because this is text-dependent speaker idea. We need to also classify the phrase. But even if we look at the single phrase and we would just do the scoring for single phrase, So if let's say that we have only this imposter correct trial, so the imposter always says the correct phrase, and we just look at single phrase, the bottleneck feature still helps us to improve the performance. So that definitely the phonetics and the conditioning on the phonemes, and so in other words, trying to compare how does this particular phoneme sound for different speakers, it is definitely there.
Yeah.
But what exactly it is looking at, I don't know. I mean, there was Shuai Wang some time ago in Brno, and we are running experiments where we try to train X vectors, where we try to do different things like training. So normally you train X vectors just to classify speakers, but we thought, shall we maybe train things as multitask and to also encourage classification of phonemes? So if we encourage classification of phonemes, is it going to help the performance or hurt, because we actually encourage the X vector extractor to also encode phonetic information? And at the end, so in fact, in the X vector extractor, you have there the path of the neural network which operates frame by frame, and it was always better to encourage there to also classify phonemes. So in the first part of the network, we would train it for in multitask training, so that before the pooling layer, you should be able to classify phonemes, and then it helps in terms of speaker recognition performance. But then the best thing was to train it things in multi-class fashion, multitask fashion, that you encourage recognition of phonemes before the pooling layer. But after the pooling layer, we used adversarial training, so that we said, and now you have to forget about the phonetic information. So if you don't forget the phonetic information, you are going to get penalized. So eventually the system should be aware of phonemes and should be able to condition on phonemes before the pooling layer, but should forget about phonetic information, about the message in the utterance after the pooling, and keep just the pure speaker information.
But that was for text independent.
That was for text independent, yes.
Which might not correspond exactly to the text dependent case.
Yeah, that's
Correct.
I think we have time for one more question or comment. One more question, sorry.
So I have one question, Alicia. So is the heavy tail PLDA working for you?
Well, it worked for, or at least it was not working better than the Gaussian PLDA for the systems that we tried here, but it still gave us some improvement when using it for the X vectors in some of the systems. But I would say that it performed pretty much the same. It just gave us some improvement with the fusion, basically. But I don't know for the rest of the tasks whether the heavy tail PLDA is giving any. I don't think it's giving much difference even for text independent speaker verification.
Thank you.
I would say we sometimes use it for text independent speaker verification. Sometimes it gives better results.
Yeah, I also did that, but I don't know. It got very tricky to get like better results. Okay, thank you.
Okay, thanks everyone. Alicia, thanks for coming, and thanks for nice presentation. Also interesting presentation. Lukas, thanks for joining if you are still with us. And I wish everyone a nice weekend and see you on Monday. Bye-bye.
Bye-bye, thank you.